make it when... Oh, I don't like microphones. Surely I'm loud enough. This one's mine? All right. Hi, everyone. Lovely of you to make it in the rain when the assignment is due. Obviously, it's very dead today in the lecture. Everyone's clearly doing their assignment. I hope that I'm about to cook you because we're about to do a lot of content in these 2 hours, so I'm sorry about that. But I would like to also just quickly start off by saying something about the assignment. There's been some forum posts that are saying, oh, you know, it's not that hard, blah, blah, blah. Stage 4 of the assignment is very hard, and it is very challenging. And sometimes it's not worth the marks, and that's okay. If you do stage 3 and you have perfect style, you can still get a HD, and that's, you know, I think when you get to uni, just remember that the expectations of marks are different to what they were in high school. It's not, you're not just aiming for, you know, the 100. 100 is going to be, you'll never sleep and you'll never eat and you'll never do anything that is fun if you just decide that you want hundreds in everything. And that's, you don't need that, right? Make sure to look after yourselves and please don't cry, even though I'm sure there's been tears shed over this assignment. And just remember as well that the days late is taken off the ceiling because we are very nice in this course. So if you do not plan to do stage 4, the maximum, and you do submit 1 day late, that just means the maximum that you can get is 95%, right? Which if you don't plan to do stage 4, you're not actually aiming for that, so you can give yourself an extra 24 hours if you want, right? It's off the ceiling, it's not off the mark that you got. But remember, anything after 5 days, it's all over. No one, we don't accept submissions after 5 days. Okay, so let's start our lecture, which is just going to cover 1,000 topics and hopefully not give anyone tears today. Welcome to week 7. You've done 6 weeks of uni and hopefully you're not all absolutely cooked. I would love, does anyone have any, for my lovely, does anyone have any sticky tape? It's a very random thing to ask, I know, but the 2 cupboards that are here they just keep popping open, which is quite annoying. Okay, so let's start. The first thing we're going to do is multi-file projects, which we tried to do through the whole of week 6 and we did not do. Was that? Oh, I would love to jam something in. Before you, like, this cohort watches me, like, pull out a drawer and get psycho. Thank you. It's because I'm so short as well, so when beautiful. Thank you very much. Okay, excellent. So the first thing we're going to do is multi-files. Woo! Who has heard of multi-files? Who knows what it is? What do you, yeah, one person.
You can call other functions from like adjacent files in the same folder or something, in the same directory?
Yeah, basically. So again, it's all about having good style, and you've seen when your assignment 1, the code is probably getting longer and longer and longer and longer and longer and longer. And it's not really, I mean, whilst you do have good style in that and we don't ask you to do anything else, it's starting to get messy, it's starting to feel messy. So multi-files allow us to kind of combat that by spreading big programs over multiple files, okay? And what it allows us to do is it allows us to also segment our programs in a way that we can reuse modules. So let's say for a particular big program, I have a maths module. I could use that anywhere else as well where I might need a maths modules, and I just plug in and plug out as I see fit by including whatever module I want into my project, right? So it improves readability because it reduces the length of the program. It allows us to have modules of our code, so it allows us to really separate our code based on what it's doing, and each module has a particular purpose to it, and then we plug them in and plug them out. And what else it allows to do is in big projects, often it's not just one person doing all the programming. That would be crazy. You would never get any sleep. It's usually multiple programmers doing project on one big program. And so what it allows us to do is it allows each person to work on their module and then to plug them in at the end and test whether or not it's working all together. So it allows us to write and test separately, and then we put it all together and test together as well. So we actually have already been using the multi-file capability. You just haven't realized it. This is just another like scanf surprise. Anytime you include the standard C libraries, you're using that capability. It means that you haven't had to write the code for printf and scanf and whatever else because you're already using the standard C library functions. And when you hash include a library, that's exactly what you're doing. You're including someone else's functions and someone else's module into your code. So far, we've only been including the standard C libraries, so the one that are available to us, and they're already available, right? There's nothing surprising about them. But now we'll be able to include our own. So we're going to be writing our own .h files, and that comes together with an implementation file as well. Okay, so basically that means that a multi-file project has 3 files, right? Well, 2 files, but there's a header file, and that's the file that defines everything, right? So you've been using them from standard libraries, but you haven't written your own, and what the header file does is it will define the functions that you're using. It might define any hash defines. It might define a few other things, and we'll talk about what it should define. It will have the comments for what the functions do. And then for each header file, you have to have the implementation file. So what that means is if in my header file I've defined a function, not defined, hopefully I'm not defying functions, that would just be insane. I've defined a function that's calculating the area of a triangle. Then in my implementation file, I would write the code to actually do that, okay? And we'll see that in action in a bit. So each header file has its own implementation file, and then you have a main.c file. Now, you've been writing this int main, and you've been using that. You know that that's the first point of entry where things actually start running. So now you'll have a main.c file, and that file is the point of entry into the program. And what we do is we really reduce the code in our main.c. That means that the main.c should not even know about what code there is in other functions. It does not care what implementation there are. It's really just it's calling out to functions, and those functions are defined in your header files, and then a programmer goes off and writes the implementation file. But the main file should not worry about what is actually in the implementation of that actual function. Okay, so we really clean up our code now. And in your assignment 2, you're going to be using multi-files to create your program. Okay, so you'll get a bit of practice using them. I promise they're not as as bad. They actually make more sense the more you use them, as I guess with everything else. Okay, so what does the header file usually contain? Okay, so the header file usually has our function prototypes, so it will tell you what is it that you need to implement in the implementation file. So it will say, it will give the prototype, which means that you'll have your inputs and you'll have your outputs and you'll have the name of the function. It will also have any hash defines, and it will have the comments to describe what those functions are doing. And it is a file that shows the programmer what it is that they need to know to write the code or to use the code, but it doesn't have the code itself that will actually implement those functions. That's in the implementation file. So it's basically a little definition, and it just allows us to have an understanding of what's going on. Implementation file, that's where you'll implement it, and then main.c, and that's where you will run things from for the other modules. Okay, so let's do an example so that you can see it all in action, and then we can see how we compile it as well. Okay, I think... No. Just 1 minute is enough for it to stop. All right, so if anyone, did I chmod it? Can you tell me if you can access it? I'll just... Let's just see what... No, I have not chmodded it. Oh my God. Trying to do things too fast. All right. So, if you look, I've created a directory called maths, and inside that maths is 3 files. There's a maths.h, there's a maths.c, and there's a main.c. So I've got my header file, which is my definition, and that's the maths.h. Then I will have an implementation file, which is a maths.c. And then I have my main file where I will call things from. Okay, so let's have a look at what the files have. Not much in there. Let's look at the header file first. Okay, so the header file has absolutely nothing in it because obviously I want to show you what to write in it. So we've got a header file for the maths modules. The header file will contain any hash defines and any function prototypes and any examples that we might want to do. Okay, so what do we want to do? I don't know, something simple. Let's keep it simple because this is not the... We've still got a lot of other things to do. That's, yep, obviously fun. What do you want to do in our maths module? I'll just... What should we do? Give me something that you want to do in maths that's super simple. Pardon? Pardon? Divide. Okay, we can do that. Although we can do that, what's something else that we can do that we can't just do with just one, like... Okay, we can do that with mod. What else can we do? Give me like a formula, a simple high school formula. A simple high school formula. Let's do like year 7, year 8. Oh my God. Okay, let's just do area of a rectangle. Let's keep it so simple, like super simple, because we don't want to do, we want the difficulty to be, oh, look at that, someone in there saying area of a circle, so they're letting me hash define a pi as well. I love that. Thank you very much. Einstein field equations, no thank you. What else are we going to do? Let's calculate the speed of light. Let's prove it. Why not? We've got all the time in the world today. Okay, I'm going to do one hash define in here, and I'm going to call it pi, and I'm going to make it 3.14. And then I'm going to define a function. Let's do one function, and this function is going to function, what's it going to be? Area of a rectangle. Okay, if I do an area of a rectangle, then what will be the input into my function? What would I need to give it? Yep, perfect. I'll need to give it length and breadth. So 2 doubles, potentially. And what would be the output? Yeah, just another double, so the actual area. Okay, so that gives me my definition. I'll have a double area. And I'm going to, no, not an int, obsessed with ints. No, not a dount, I don't know what that is. Double length and double breadth, not breadth. You know, just like you, I'm struggling to put a sentence together today, so hopefully everyone's going to enjoy that. I don't know what I'm going to make mistakes, what other mistakes I'm going to make today. Okay, excellent. So we've got that. Amazing. Why don't we do something else that's really simple? Why don't we do a sum? How does everyone feel about a sum? Just to show you two things, and this one I'm going to do, okay, so we'll do function, that will do that sum of two numbers, and so the output, let's just make it an int. Let's make this a really unflexible function that can only add two numbers that are ints. I need a sugar rush as well. Okay, amazing. So we've got two functions. We've defined them in our .h file, so our header file has the definition of them. I'm going to save it. So now we're going to go into our implementation file, and we're going to implement them. So this is my maths.c file, and it kind of goes hand in hand with the maths.h file because it needs to implement whatever is happening in that .h file. Okay, so we know already we do our hash include off just the standard library. But now how do we include our own header file? Okay, so to include our own, you still use the keywords hash include, but instead of doing the less than, greater than symbols, you put it in double quotation marks. And my header file is called maths.h, so I will include it by putting it in double quotation marks. So that's going to give me the definitions and the prototypes that I've given in maths.h. So what it will do when it has this hash include maths.h is when it compiles, just think about it, it will take all of this and it will place it on top of this file, right? So again, for humans, we want to spread this stuff out because humans have a hard time processing so much information all at once. So we want to improve the readability of things. But a machine doesn't care. So when it produces its file, it just makes it all together. Okay, so we've included our maths.h, and now we want to actually have the two functions. So my first function is so I no longer have a main.c. That's going to be inside my main.c file. And I have the definition of this. And from this one, I will just return length times breadth. Yep. Everyone happy with that? And similarly for my sum, we should do the area for circle. It would, okay, next we might do that. Okay, and here I'll return num1 plus num2. Okay, excellent. So that's implementing the two functions that I've defined in my maths.h. So now I want to look at my main.c, and inside the main.c is where I actually call these functions and use them. Okay, so I've included my standard input-output because I might printf something, and then I'm going to include our header file also. So I need to let this main.c know that I need to use the functions that are defined in my own library that I've created, so maths.h. So I'm going to include my header file in both the main where I use it and in the implementation file for whichever header file I'm doing. Okay, so I'm going to give it two numbers. I'm going to give it a double sorry, I'm looking at the conversation online. It's usually a 2-week turnaround for assignment return for you. And it's not that quick that you just do the style. We look at a lot of things when we look at your code. Okay, so we've got two numbers. We've got the first double. Let's have it length. And we're going to assign the value, I don't know, 3.1 to it. And then let's do a breadth, 4.5. Amazing. Let's have some ints as well. Okay, amazing. Okay, Okay, now we need to call some functions and then we print out. So I'm going to printf and I'm going to say the area of the rectangle is blah blah. And here I'm going to call my first function, which was that area function, and I don't actually remember what the name of it was. Area, REC, okay. I'm going to call the function and I'm going to give it length and breadth. And then oh my God. Any day now I will succeed in doing a semicolon. There we go. And then I'll do the same for the sum. What mistake have I made that no one's picked up? Pardon?
You put int in there, but you're trying to print dollar.
Perfect. Well done. I've forgotten what was it called? Sum? Yes. Okay, amazing. We've got all of this going on now. So what happens now? Let's compile. So what do you reckon we compile? Yeah, we compile a main. Absolutely. Do you reckon we compile anything else? Maths.c, someone saying? Yep, absolutely. Okay. Let's compile. So we compile all of our C files. And then we run them. Okay, so I'll run the maths, and it will give me that the area of the rectangle, which I assume is correct, is that, and the sum of two numbers is 12, which I can do 4 plus 8, so that's, I can assure you that's correct. Amazing. So when you compile, you're compiling all your .c files, and the reason you don't compile the header file is because it's included in all of your files, right? So when you compile the .c files, the keywords #include.h, it will go and find that and put that on top, right? And you don't compile the standard input-output header files or anything like that. So we don't compile the .h files, but we compile all of our .c files that we're going to use. Okay, how's everyone feeling about multi-file projects? Everyone's like half falling asleep, half dead in this audience. It's amazing. Thank you, Bree. That's the kind of, you know what, Bree, can you just throw some chocolates, give them a sugar, like some sugar rush, something, because come on. I've had to come here today, and it was raining. I hate it when it's raining. But also love it because we need the rain for plants to grow and for food. Oh, that was just that was an amazing catch. I appreciate that. Sorry, Bree, you're going to have to, I think, go on the other side as well. Otherwise, it's not fair to this side, which is actually more full than the other sides. Someone is leaving. Oh, my goodness. Oh, no, they're moving closer. That's okay. I forgive that. Actually, forgive anything in week 7. Week 7 is when it's all over, really. Okay. So every week 7 lecture, everyone asks about the assignment. Okay, so let's do a poll. Can someone do me a poll, please? How are we feeling about multi-files? Move it on. It is so handy. Thank you. Yes. And you are not going to like them in assignment 2, but you will see a purpose for them. Just like pointers. Is someone doing that poll, or am I just... Okay, in the audience, not the online people, because online people will do it in a second. Give me like a hands up if you're happy with multi-files for now. Yay! And I'm going to, when I do linked lists, I'm going to start in one main, and then I'm going to break it up into multi-files as well, so that we can get more practice using multi-files. So it's all happening. Okay, then let's move on, which is so exciting. And I'm just going to, I'm going to go crazy today, giving you, I don't even want to rehash malloc, but I'm going to have to. Malloc, who feels anything towards malloc? Love, anger? Just positive emotions over there, John? Yeah. Who remembers malloc from last week? Who wants to forget malloc? Yep. Yay! Thank you. Okay, so malloc is this lovely, lovely function that we have in front of the standard libraries. Oh, someone's indifferent to malloc. You won't be soon. Soon you will be hating it, or no, you'll always love it, actually. Malloc allows us to feel empowered by letting us decide where memory goes and letting us allocate that memory and basically letting us play with memory. So whenever we malloc a piece of memory, we put it on the heap in the storage, which means it kind of goes anywhere all over the shop. It doesn't just look for the next consecutive spot of memory. So it means that we kind of have to know where that memory was given, because it's in a heap, like my, so the return of that malloc function is a pointer to the address of where that memory that has been allocated is sitting. So what malloc allows us to do is it allows us to create memory dynamically. So it allows us to create memory as we need it. So with arrays, we're always kind of stuck in a certain size. There are ways to reallocate arrays, but they're also not that dynamic, right? So it means that we often waste space with arrays, because we'll say, okay, I'm going to have an array 2,000 ints, and then I use only 2 of them. Well, that's I've used up 2,000 spots of memory as opposed to 2 spots of memory. So malloc allows us to do that dynamic allocation, and it means that we are in control of what we allocate, which means that we then have to not just allocate, we also have to remember to free that memory. So whenever we use malloc, we also have to use free. Okay? When we control it and we are holding on to it, we want to free that memory up so that we don't have a memory leak. A memory leak is when we forget to free and that piece of memory just sits around and the memory is lost and it cannot be freed. So we don't really want to create that. Okay, so we've got malloc and free, and then if you remember from week 6, we need to give malloc whatever size we want. So we need to let it know how much memory we want to hoard. And we use the size of function for that. The size of function allows us to establish the size of the memory that we want to have. So again, when we call malloc, we will have its return is a pointer to the piece of memory that you have created, well, that has been created for you, malloc, and then we say what is the size that we want of that memory. Okay, so now we're going to look, I'm not going to go back to pointers in a second because I'm going to do linked lists, and when I do linked lists, we're going to revisit pointers, and we will revisit pointers again, but for now, it's going to be in the context of a linked list. But I want to talk about structs and accessing struct pointers. So back to code, and I'm going to have to create a file because I don't know what happened. The file is in a different week. Oh, it's in a different week. This is how much I thought we would cover in week 5. Okay, so usually, that's not where I wanted that. Usually, how do we access our pointer, how do we access a struct, a member of a struct? What do we use? A dot, exactly. Now think about if I have a pointer struct. To access it, I would also need some brackets, right? Because I'd have to dereference, and then I'd have to access the struct, whatever is sitting inside the struct. So if you remember, dereferencing means that go to the address stored in the pointer and find out what is sitting at that address. So that's dereferencing a pointer. I should have really done a rehash of pointers, but alas, we will do it as we do linked lists. So this is going to be more like a syntax thing, right, for the struct pointers. So that's why I just want to cover it quickly before we move on. Okay, I don't know why I created this unseemly example that has way too much complexity under the sun, but it's happening for now. So let's say I've got a Lego piece. It's clearly because I was doing Legos. Okay, and it's got 3 things in it. Oh, I really don't want it to have that. Anyway, it's having that. So it's got a name, and then it's got a double price, and it's got an int pieces, okay? So this is my struct Lego. It's composed of 3 things. I've got an array of characters that is the name of the Lego. I've got a price of it, which is a double, and I've got an int, which is the number of pieces that it's got in it. So in the main, I really just want to access those members to show you how you do it when you have a pointer struct. So first of all, I'm going to declare a struct. So let's do a struct Lego. So struct of type Lego, and I'm going to call it my Lego. Okay, great. So I've got a struct of type Lego, and it's called my Lego. Now, I want to do a few things, and I want to have a pointer, right, which is amazing. So if I want a pointer that's pointing to that struct, the pointer is pointing to a type of struct, so it's going to be struct Lego. Things are going really well today. Struct Lego. Now to use a pointer, right, we do our beautiful star, so it means that we are declaring that this is going to be a pointer, and that pointer is going to be pointing to a struct Lego. And I'm going to call it my Lego pointer as the name. So that means I've just declared a pointer, and I've declared it. I'm now going to assign it the address of this my Lego where it's sitting. So this Lego over here. Yep. How's everyone feeling? Thank you. There's just one person that's like, thank you. Everyone else just wants this to be over, I think. It's okay. You've got 4 more weeks before it's over, so you really still have to pay attention, and we're about to do the other hurdle in the exam, the linked list part. Okay, excellent. So we've got a pointer. It's pointing to that my Lego struct, and we've given it the address of that. Now we want to initialize the struct, okay? That means we want to put some things into that struct because right now it's all empty, right? So I could do it if I were doing it in a way where I didn't know a shorthand way of accessing a pointer struct. The way I would do it is I would have a dereference of my Lego, yeah, which means so dereference my Lego pointer, which means go to the address in here, okay? And then I would want to do a price, for example, okay? And then the price, the cheapest Lego you will ever find. So that can get pretty messy, can't it? Because I've got to dereference it, then I've got to access the member that I want, so on and so forth. So we can really kind of get messed up with all the brackets. Plus we have all the other brackets that are available to us. So readability is very messy. Everything is messy. Too many brackets. Close, open. So we do have a shorthand way of doing this instead of having to dereference the pointer and add the brackets because I have to dereference it first, then access the member of the struct. So instead of doing it like that and having that mess of a thing, what I can do instead is I can use an arrow. And that arrow basically means dereference and, hey, Yeah, so, and then just price, yep. So this arrow over here basically means the same thing as dereference and go to it. So access, the arrow is saying it's a pointer struct, and then access which member of that pointer struct. Okay, so it makes it much easier to interact with pointer structs. Okay, and the same, I can do exactly the same. So my Lego pointer, and then I can dereference it, and I can assign something to pieces, and it's got 450 pieces. Amazing. Okay, and then what happens with the name? How do can I do this to the name? Can I do my Lego pointer name? Can I do that? And then just say, okay, is equal to, I don't know. Can I do that? No. Thank you. Who else thinks no? One other person thinks no. Third person thinks no. Fourth person thinks no. Yes, no. You cannot do that. Why can't you do that? Yeah. Oh. Where? Yep, thank you very much. Yep, just saw it. Yep, PTT now. Good. It's a worry when you can't put 3 letters in the order that you require. Okay, why not? Why can't I assign it like that?
You can't just assign a string to an array because you need to single one to
Yeah, exactly. So just a quick rehash on strings. We cannot do that because this is an array of chars. So we can do them one by one and go slightly insane if that has 120 characters. But what we can do is we can use a function called string copy, which kind of does it for us. So again, this is why those libraries are so handy, because they do things for us and save us a lot of time. So I'm going to use the string copy function, and I'm going to copy into that part of it, and there we go. And so this function here, string copy, is sitting inside my string.h library, which I've included. And what it does is it actually, the function itself, when it's implemented, it does them piece by piece, char by char actually, copies it into that, that array of characters. Okay, amazing. So now I've loaded up, initialized my struct pointer. So now I want to access those bits and say what it is. So the Lego something string, so again, oh my goodness. Nope, here we go. Okay, so again, we're going to access that Lego pointer, and we want the name for that. So again, that arrow means dereference this pointer, which means go to that address, go to the address that is stored inside my Lego pointer, and find out what is sitting in it, and then access the name member of that struct, because there's a struct sitting in it. So I need to specify which part of that struct I want. Okay, excellent. So I've got the name, and then the next thing I'm going to want is the cost. So I'm going to have the price, and then the next thing I want is the number of pieces. Okay, let's see what happens. I'm like, did I spell something there wrong? No. Okay, and it's giving me the Lego books cost $12.60 and has 450 pieces. So the most important part of that piece of code is using that, I really hate the name of the arrow, so I keep calling it an arrow because otherwise it's got an awful name. So the arrow, you're going to be using that arrow a lot for the next 4 weeks, like all the time. So it will be so fun for you guys. So fun. Okay, so how do we feel about that? I'm moving at like the speed of light because no one's saying anything, so I might as well. Thank you very much. 1 thumbs up. Just 1. 2 thumbs up. Yes. 3, 4. Yes. 5. Thank you. I mean, you had a chocolate stolen from right in front of your face, so I'm impressed that you can even thumbs up now. Okay. Can we have another poll, please? Because I want to see how the people online feel. That will not tell me if they don't understand. All right, I'm just considering whether to start the linked list now or to give the 5-minute break now and then do the linked list for an hour. That's probably the smarter way to do it. So let's have a 5-minute break right now. And then when we come back, we're going to start the linked lists. And you guys just tell me on the poll how you're feeling. And don't worry, we keep rehashing everything every lecture, so don't worry. Start it again. Got this. This is now linked lists. This is the best part of this course, I think. Yeah. All right. Who's heard of linked lists before? Yay, a few people have heard of linked lists. Linked lists are amazing. Okay, so now that you've maybe become comfortable with arrays, or maybe you hate arrays, or maybe you just never want to see arrays again, sorry, but that's not going to happen. They are now a part of your life. And now you're going to learn about another important data structure, and it's going to be the linked list, okay? So arrays, they are not, a lot of wastage with arrays. I've talked about it before for memory. Linked lists allow us to kind of move past that. Now, in this first course, in the foundational course, you might not really see the where will I need to use an array, where will I need to use a linked list. That might not become obvious yet, so don't worry about that yet. It will come together as you keep doing programming, and you will see that some problems are better suited to different data structures. Okay, so what's so special about linked lists? I mean, everything. I get to draw. That's the most special thing about them, even though I forgot my pencil today, so I don't get to draw today. But they are dynamically sized, which means that I don't waste memory. I just request a bit of memory every time I need to add something to the linked list. And when I don't need it anymore, I delete it from the linked list and free the memory. So that means, again, I'm not wasting any memory. So each element of a linked list, so each part is called a node. And that node contains some data. But unlike an array, if you remember, all elements of the array are stored in a memory consecutively, one after another. So if I access array at 0, I know, and it's an int array, I'll know that the next piece of memory will be 4 bytes later. And they are contiguous to each other, which means they come one after another, and it allows me to know how much memory I want. This is not the case with a linked list. A linked list is like a scavenger hunt, which is fitting because Easter is coming. So, although you're probably all too old to scavenge for Easter eggs, but who's too old to have chocolate? I don't know. I don't actually like chocolate, so maybe you are too old. Okay, tangent. So linked list nodes, they are not stored contiguously. If they are, it is a complete fluke. But basically, you need to be able to find them somewhere in the heap because they're just like thrown anywhere, right? Where there is a little piece of memory, that's where that memory is taken, and you need to know where that is. But what that also means is that as part of your node, you can't only store some piece of data, you need to know where the next portion of the linked list comes from. Because otherwise, I will never know this because they're not one after another. They are scattered all over. Again, the good thing about it is, let's say if I have an array and I need to remove, an array has 100 elements in it, I want to remove the 4th element, and that means that I have to take everything after it and move it backwards, and it's quite difficult to kind of shrink an array or remove things, whereas in a linked list, I just remove that node and connect up 2 different nodes to show a different progression. So I don't have to worry about size. I just dynamically call up and make a node as I want it. I dynamically delete a node when I don't want it. Basically, I'm in charge. And much easier also to change. So in an array, if I want to change up the order of the array, it requires me to play around a lot with where the elements go, copy the elements that come afterwards. It's a bit of a drama. Whereas in a linked list, I can just change where the next node is pointing to, and it allows me to change the order of my linked list however I want. Now, one good thing about arrays is if I have an array of 50 elements and I want the 25th one, I just say array, in brackets 25, and that allows me to access whichever element I want, however I want, and that is because they are stored in memory contiguously, which means I can easily calculate where it is that I need to be to access that element. And that is not so in a linked list, because in a linked list, I only know where the next node is. I don't know, well, it depends what kind of linked list, but the linked list that you're learning about in 1511 is just a single way linked list, which means it goes from the start to the finish, and each node only knows where the next node is. So it's like when you go on a scavenger hunt, the clue tells you where the next spot is. So I only know where the next thing is, which means that if I need to access the 4th node in a linked list, I have to start at the beginning, go to the first one, go to the second one, go to the third one until I get to the 4th one. So I can't just pick and choose where I want to be in my linked list. Okay, where is it used? Web browsers is a good example. When you click back. Music players, playlists. Anyone else can think of any other examples that kind of like throw linked list vibes at you? Scrolling TikTok? Yep. You should not be doing that. Just a quick 2-hour waste of time at night. Also guilty. Anyone else? No? Pardon? Undo. Undo's a great one. Absolutely. Yeah.
Maybe a dungeon game, like entering another section or another map.
Maybe. Could well be. Yeah. Depending how they store it. But basically, it's something where you can bit of movement back and forth, and you've got yourself a linked list. So I'm going to draw it out for you, and because I forgot my pencil, it's going to be a diagram on the lecture notes. All right, so what is a node? A node is something that has a piece of data in it. That data does not have to be an int. It can be a char, it can be, I don't know, it can be whatever you want it to be. It can be a double, it can be an array, it can be anything. It can have multiple pieces of data as well, because a node is just a struct. So just when you thought structs are done, assignment 1 is done, I'm good to go, you're not good to go, you are now in complete and utter struct land. So a struct, and the reason we want a node to be a struct is because we're keeping two different things in that struct, okay? One is some piece of data, or it might be multiple pieces of data. And for our single linked list, it is another struct node pointer. Here we go. This is why you'll be using pointers a lot now. And the pointer has the address of the next node. So what I was saying, because nodes are allocated dynamically, they could be anywhere on the heap in memory. You need to know where that next thing is, because they're not right next to each other. So each node has some data, and then it also has a pointer to the next node. So it's telling you where this linked list is going to next. So, and we're going to use int to start with. So we can create a linked list by having many nodes chained together. Yeah? And the first one is going to have, they all have the same thing because they're all from the same struct, right? So we define what that linked list looks like. Each one will have some data, and it will have a pointer to the next node. And that pointer to the next node is just going to point. So not a good diagram because I drew them linearly, one after another. Just think of them like displays. They're all over the shop, right? It can be one node's here, one node's there, one node's here. So you need to be able to point to where the next one is. Okay, fantastic. How great. But my first node is also sitting in a heap somewhere, who knows where. How do I know where the linked list starts? Yeah. Yeah, so when I malloc some space for that node, yeah, I get a pointer to an address. And that might be either a next node or it might be the start. So the start of a linked list, the first node is called the head of the list, okay? And then the end is called the tail. Super creative names. Yeah?
The tail node would not be having another struct node next to it.
That's right. So the head node is not actually a node, but it is a pointer to the first node, if that makes sense. It basically just has an address of where the list starts, okay? It's not a node in itself, it's just a pointer to the first node. So to start the list, I'm going to have just an address of where my first node sits, and it allows me to know where that list starts. And then I can follow it along, follow it along, follow it along, but then I need to know where this linked list is finished, okay? Because it doesn't go forever, right? How do I know when it ends? Who knows? Just take a stab. Yeah. Next node is going to have. Exactly. It's not going to have anywhere to go. And what do we call this blank space? Take a poke. You've had a few times. A void, but it's not a void. But what's another thing in programming you've used where it's like a blank space? Yeah. Null. So in memory, a blank space is a null, okay? So you finish a linked list by saying, okay, the end is going to be pointing to a null. So hopefully that's now kind of coming together that if we want to traverse the list, which means if we want to go from one element to the next, we know when to finish our loop, because our loop needs to finish when we are accessing null. Well, hopefully we'll never access null, because if you access null, things are not going to go well for you. Yeah. You have a circular linked list. It's not, yeah. So there are different types. There is a double linked list, which it stores the previous and there's different types of linked lists, but you're only going to learn single linked list from beginning to the end, and that's that, okay? So, yep. Okay, so this kind of gives you the idea that you now have a way to loop yourself and be able to stop somewhere, okay? But you don't want to access a null pointer, because if you try to access a null pointer, what do you think happens? If you try to access a piece of memory that doesn't exist, it's going to give you an error. It's going to give you a nasty error. Yeah. It is, and it is the nastiest error that C can give you. And it's because when you compile with a standard C compiler, it just gives you segmentation fault. And that's it. Imagine you've written 3,000 lines of code. You are not told where that error has occurred. You're not told what has caused that error. And you're back to square one. All you get is those two words, segmentation fault, and good luck. DCC does not do that, so you should be thanking the DCC gods. DCC actually picks up where that error has occurred and tries to direct you to where it is, but you are not going to have DCC forever. So you really want to learn to prevent them and to not access null pointers. And that's also, yeah, well, there's been some big cases of where this has caused some serious issues. Okay, so let's have an example. Let's say we have a list, and the list has the numbers 1, 3, and 5. Amazing, okay. So, and we create some nodes. The first node has the address 0xFF0. It means I'm going to have a pointer called head, and the pointer is going to store the address of that first node. Now remember, a pointer is just another variable, so that pointer has its own memory address as well that I don't really care about right now, but it is its own person. It's an individual. But the head is just going to store, it's not a node, but it's storing the address of the first node so that I know where to start my list. Okay? So then the node is going to have the element 1 in it, the data 1, and it's going to point to the next address. So 0x, these numbers are completely made up. Okay, so it's pointing to A44. A44 is here, which means that it's going to go to the next one. And the next one's going to have number 3, and it's going to point to 3B4 as the next one. So then 3B4 is going to, this is our node 3B4. Now 3B4 is going nowhere after this, which means that it's pointing to null as the next one. And it's saying that this is the end of the list. This is the last node in the list. Okay, so should we create a list? How's everyone feeling? Does everyone theoretically kind of understand the list? And I actually think lists are easier to understand for some reason than arrays. I don't know why. And sometimes easier to implement because they're very methodical to start with. You might make a lot of mistakes and not actually have an understanding, but methodically they're much easier to do. And you build that understanding from just doing it in the same kind of way over and over again, which you will be doing a lot in assignment 2. Okay, can we do a poll as well? Just a quick little poll. How do we feel about the theory of a linked list? All right. How exciting, our first linked list. Oh, okay. I hope that this, yeah. Okay, so the first thing we want is we want a node. Okay, we want to define what a node is. And each node, what makes it a linked list is that it has a next pointer, right? This is what makes it a linked list, is the fact that it's defining what comes next in the list, so what's chained together. And I also want to have some sort of data in it, so I'm just going to call it int data and then a struct node next. Doesn't have to be an int. It can be any other data variable, right, as long as it's a variable. But what makes it a linked list is a pointer to the next node. Okay, so we've defined our struct, a single node of a linked list, but we haven't actually done anything yet. Okay, there is nothing happening obviously because I've left it to do in the lecture. But what I think we will do is we're going to do some functions, and we're going to do them now. We're going to do some functions. So the first function we're going to do is, unsurprisingly, to create a node. Okay, so what do you think in such a function I would need to give to this function to create a node? If my node is defined as having some sort of data and a pointer to the next node, what do you think I would need to give that function? Yeah, I need to give it some data. So I'll need to give it an int for the data. And what else do I need to give it? Yeah, I'm going to need to give it some sort of pointer that is going to give me the next node. Okay, so I'm going to give it an int, and I'm going to give it a struct node next, really. And what will the output be? What will I create? I'm just going to create a node. Yeah, so it's just going to be a node, which means it's going to be a struct node. So by definition, that means that my node is going to be a struct node, because I'm creating a node and I'm returning that node. So I'm going to create a struct node. And because it's a node, I need to return where that node is sitting. So it's going to be a struct node pointer is what I'm returning. Yep. So struct node, I'm going to call the function create node, and I'm going to give it an int data, and I'm going to give it a struct node next. Okay, someone's asked a great question. Can you use type defs? You can use type defs if you know what they are. I will avoid using them in 1511 because they confuse the living daylights out of someone who's just starting to program. But you can use them in the assignment if you would like. Okay, excellent. I don't know why I did that. I'm not ready to make this function yet. This is just my prototype for this function. Okay, great. I'm going to need to print this list as well. But I'll need to create it first. But I'll need to print it. Okay, what happens if I have a function that will print the list? What do you think I need to give that function? Yep. Well, let's go easier. What would be the output of a function that prints something out? Hey? Well, what would be like if I were defining it in my definition of the function? Would it have an int, a struct, a pointer? Someone said it from there. Someone said void. I heard it. You're just printing stuff out. You're not returning anything. So the output is void. Yeah? And if I want to print out the list, the only thing I need to give that function, and the only thing that allows me to, how do I know where that list, what do you think I need to give it? What was I saying before about the list? Once I know where it starts, I know everything else about it. Kind of. Yeah, I need to give it a pointer to the start of the list. So I need to give it a struct node head. I need to give it the pointer where the head of the list is sitting. Okay, excellent. So the print function will look something like void print list, and I'm just going to give it a struct node head. Okay, I think we're going to leave it at those two functions, and that's going to be us for this whole lecture maybe, or maybe we have time for more, who knows. Okay, so the first thing I need to do is I need to get some memory, okay, because I'm going to create a node. Now, who remembers what we do to get some memory? Yeah, I'm going to malloc. So let's call our function, because we've got a function, so why not? So I'm going to create the head of the list. So I'm going to say struct node head is equal to, and then I'm going to call create node. And what did I want the list to be? 1, 5, and 17. Anyway, it doesn't matter. Let's give it the data 1. So create node wants a data, and then it wants a next node. What's going to be my next node if I'm creating one node? I don't have any other nodes right now. No, right? Because I don't have anything else right now. I just wanted to put that in, and then I will link them up. Okay? So hypothetically, this allows me to, so I've got a pointer. I've declared that I have a pointer. The pointer is called head. The pointer is of type struct node. And I'm calling the function create node with values 1 and null. Okay? So what that means is I'm about to, and the create node function returns a pointer to a struct node. So it will return an address to me. So let's write our create node function. Okay. So someone said before that I need to malloc some stuff. I need to malloc some space for this node. That's how I create a node. So to create a node, I want to malloc some space for the node. I want to initialize the node with values. And then that's my node. And then I'm going to need to return something that's going to be that node. Okay? So the first thing I'm going to do is I'm going to malloc some space for the node. So I'm going to malloc, and I need it to be, I'm going to use the size of function. Size of what? What am I mallocing space for? For a node. So what do you think I need the size of? Sorry? So you want the size of? Not data, because data is not enough. My node has data and a pointer to the node, to the next node. Yeah, so it's struct, which struct? Struct node. So I want the size of a node because I want it to contain the int and also a pointer to the next one. So I'm going to malloc the size of a struct node. Okay, fantastic. Now who remembers what malloc returned to me? Cooking you slowly. It did return a pointer. Excellent. Okay, and it returned a pointer to the node that it has created. Okay, so I'm just, how struct node, let's just call it new node. How does that sound? So I've created a new node, and it's a pointer, it's of type struct node, so it's pointing to a struct node address, and whatever is happening in there, the malloc has created some space and it's popped that address in that new node. Okay, now I want to initialize it with some values. So my new node is called new node. It's a struct pointer. So who remembers how I access an element of that struct pointer? Yep, with a little arrow. And the first thing I'll do, I'll pop some data in there. Now remember, I have called this function create node and I gave it the data. So that means that I want to assign the data to it, that I have called it. So I've called it over here and I've given it data as one of the inputs. So I will initialize it with that value. And the same thing for the struct node next, which I had. So that my next, because remember struct node has data and it has a pointer next. So I've assigned something to data. It was the data that was given over here. And now I have this next thing here. So I'm going to assign it into the next. So now this node has malloc some space, which means that it's created. Who wants me to draw it up? Thank you. Yep. Who remembers what the latest thing that I installed on my computer? Hey? Oh, a whiteboard. Do you know what the problem is? Sometimes the stick is not long enough for me. I'm shaped like a 12-year-old. Please don't all rush out to help at once. It would have been funny if it just like went back up. This is a very tall stick. I need this for home.
I can put the stick back.
All right. Okay, so what have we got? We've got a bit of code. We've got a create node. So the first bit, the on line 41, it creates a node. So we malloc some space, and when we call malloc and we say size of struct node, what it does is it grabs and it creates enough space somewhere in the heap. So imagine that this is whole heap. I'm really neat drawer, so good luck with that. And there's like lots of space here, whatever, there's something there. It's created this one node here, and the node has an int data, and it has a pointer to the next node. This is tiny. I don't know if you can read that. I've just realized how small that would be. Okay, so the malloc has created this pointer for us. And then it said, okay, and store the address. Let's say this pointer is sitting at this address. So it said, okay, pop the address into this new node variable. So my new node is a pointer to a struct node, and it now has the address of this node. Okay? And then I say, okay, new node, and I use that stabby arrow, and the arrow basically says dereference new node and go to the data element. So dereference it, go to the data, and make it equal to the data that I sent to it, which was number 1. So it places that in it, and then the next line says new node, dereference the next element. So dereference in here. So go to this address 0xAAA, dereference this one, and then place null in there. Because next was given, that was the null that I send it off with. Okay? So now I have one random node, and this new node pointer has the address of my node that I have. Okay? So what do you reckon this function would return? Oh, that is not that great. Sorry, that was very small. For next time, I'll go bigger. Okay, what do you reckon I need to return from this function? How do I know where this node is that I've just created? What tells me? Which element of this function tells me where this node is? Kind of close. Just my new node. My new node has the address of this pointer that I've just, has the address of the node that I've just created. So if I return new node, it now means that I know where this node is located in memory. So I'm going to return, oh no, and this screen just went off. Hang on, sorry, now I can't see people online. Okay, so I'm going to return the new node. And what that will return is it's returning that pointer to a struct node. It's returning an address to a struct node. It's returning that 0xAAA or whatever it may be. So I now know where that node is. Okay, fantastic. And if I go back to this function, when it returns this new node, so this function is going to return the address of the new node, which means that inside the pointer head, I now have this 0xAAA stored. Okay? So I am now saying, okay, this is now the head in my main function. Who's napping? Who's still good? I'm glad you guys are good. Yeah, you've heard this content a few times. Okay, excellent. Okay, great. We've made a node. No one's excited. There's one node, and it's sitting somewhere in the heap. And yes, a clap. Thank you. We made a node. Okay. Now we want to make some more nodes. Sorry. A list needs a few things in it. We need to chain up a few things. So we want to add one more thing to this list. Okay? Now, let's think about it. Okay? Let's think about it. This is going to break you because sometimes I want to create one more node. And where do I want to put it? I do. What was the list? I've forgotten. I mean, it doesn't matter. 1, 5. Okay. I want to create a new node, and I want that node to have 5 in it. And I should have gone backwards on this node. Doesn't matter. Well, it does matter. Let's count backwards. I want to insert at the head. Okay? Hey? Yeah. I tried to keep it simple, and instead, I've gone the opposite way. Oh, okay. We've got one thing in our list. Why don't we print it out? How do we feel about printing it out? It's exciting. We can see what's in it. Then we can see if we're doing the right thing. So let's do our print list function. Okay. All right, and so we've got a linked list. This is the head of the linked list. It's pointing to nothing, which means that over here right now we have a big fat null. It's pointing to nowhere in memory. Okay, and now we want to print out the list. Okay, now when we send out our, when we make a call to our print list function, we give it the head of the list. Okay, so we give it that first node because then we should be able to follow it from one to the other, to the other, to the other. Okay, right now, easy peasy, we only have one node, so things are really good. Now, actually, I'm just going to do it with the head, and then I'm going to change it for you when we do a few more things, just so that you can see why that's happening. Okay, so I'm going to do while, and my pointer is not equal to null. And we will change that. It's not good practice to kind of play around with the head of the list because you're gonna lose what's going on. So so remember how I said when we saw that it finishes on a null, it gives us a really good way to loop through a linked list and to see where it is that that linked list ends. So basically this while is saying while we have not reached the end of the linked list. So whilst the head is not equal to null, whilst there is a next address to follow of the linked list, I want to just print out the node. So I'm going to printf, and I'm going to printf a node. And the node is inside my pointer head. Now I want to dereference that pointer and access which element of that struct? Data. Excellent. So I want to print out what is sitting inside my data, and then I want to move my linked list along by 1, right? How do you think I would do that? How do you think I would go to the next node of a linked list if I were to have one? Next, yeah. Yeah, perfect. So my list would now have head next. So I've moved it along by 1. Okay, so the new, okay, this is so horrible because I've used the head and I don't want to use it anymore. So I'm actually going to fix it now. Okay, why do you think it would be a bad idea to move the head along and to keep increasing it if I'm playing around with a linked list? Yeah, well done. So if I keep moving the head along, I no longer know where that list starts, okay? So I've lost the start of it. So usually, good practice is to take that head that you have and to assign it to a different pointer. So what I've done is this pointer that's come through here, I've got a struct node current, okay? And this current is an excellent way in a linked list to keep track of where I am sitting, which node I'm sitting on currently. So I'm going to change everything to current. And that means my head is safe, well, somewhat. And I've got this lovely current keeping track of things. So let's compile it and let's see it print out just that one node. And then we will pop in a few more. Okay. Oh, how exciting. Okay, that doesn't matter yet. It's going to be used. It's only because I have one element. Do you know what would have helped? Why didn't it print out anything? No, I have. But why do you think it printed out nothing? I did not call the function. Yep. Nope, that would be all too much. I did not actually call the function. So I'm going to call the function print list, and I'm going to give it the head. Okay, let's try it again. Ah, it's working. It's going through the list. It's one node of the list. It's printing out one thing. Okay, great. I think this list is feeling a bit lonely with its one node, and it needs some friends. Needs a few more nodes in there to make it feel happier. So let's do our next node. Okay. We're going to create one more node. How do you think we will do that? Nope, we can keep calling that create node function. And you know what? I'm going to modify the list. The list is going to be 5, 1. I'm going to go backwards. This is the list that I want to do, because I haven't taught you how to insert at the bottom yet. Okay, so I've got number 1. Number 1 is pointing to null. This node exists. So if I create a node with the value 5, okay, well, we know that I'm going to call up this create node, and I'm going to give it the value that I want to insert in it, so 5. What would I point it to? Because from 5, remember, I'm going to give it the next. So from 5, I want to go to 1, head. Excellent. So I'm going to give it the head as the place that I want to point to next. And where do you think I'm going to attach things to? Because now I want the 5 to be the start of the list. So what do you think will be something here is equal to? And I want this node to be the first node in the list now. Head, okay? So remember that this part of things is executed first, and then it's assigned to the left side. So the right side is done first, which means I'll create the node first. I'll pop a 5 in it. I'll give it the value of the head next. And then I'm going to assign whatever values returned from here. I'm going to assign it to here. So if we're to see it in action. This is an exhausting lecture. Okay, so I've got no, you know what? I need my create node function so I can see. First, let's do it from here. I really like to draw on the screen much better. Okay, so I've got my create node. I'm calling my create node function. And I'm giving it the value 5. I'm giving it the value 5, and I'm also giving it head. So 0xAAA. Okay, excellent. So I do the right side first, so that means I'm calling this function. So let's go down to this function and see what it does. Okay, so this function is doing 3 things. Struct node, new node. So this is my data. This is my next. I wrote small again, I'm sorry. Okay, new node, malloc, size of struct node. Excellent. I've created a new node somewhere here floating about, and it's got the size of a struct node. So again, I've just created a struct node. And this is called a new node variable. The address is stored inside my new node. Okay? So that means this is now going to be storing my new node. So that's the first line of code there. Then I access new node, the data part, and I assign whatever's sitting in here to it. So I'm going to pop 5 in here after I dereference it. And then what I'll do is I'll access the next, and I'll assign whatever is sitting in here in it. So 0xAA is now going. So I've got a lovely new node. It's pointing me to this node over here. So I do have a connection. I haven't lost that node. And now I go and return the new node. So what I'm returning to my main function is I'm returning this address over here. And when I return that address, what happens is that address is returned by this function, and it's assigned to head, which means that my head is no longer here. This is now my new head. And this head has the pointer, so I haven't lost my function. It's pointing me to that one. So that means I start at 5, and then if I go through the linked list, I get to 1. So if we were to now run that, I'll get my 5 as the first node, and then I'll get my 1, which it was pointing to. Yeah? Yep. Thank you. Yep. How's everyone else feeling? Okay. 2 thumbs up. Thank you. Thank you. All right. Should we do one more? And then let's add a 7 and we'll run through it as well. Okay. So if I want to do another part, another node, and again, I want to do exactly the same thing, I'll say head create node, and I will call that function with a 7, and I'll give it the head. So what it means is I'm inserting at the head of the list. So let's say now I'm calling, there is. Okay, so now I'm calling the function with 7 and head, which means I've now called this function with the data is 7 and the head. So, and the head is 0xBBB right now. So I've called this function again, and now I've called it with these values. And let's go to that function and perform what the call is asking us to do. So we go back to here. First line is create node. Malloc some space for it. So again, I'm going to malloc some space, and I'm going to malloc the size of another node. So I've got another node happening, and this node, you'd be surprised, is named 0xCCC at the address. Okay, so I've malloc some space for it, and I've assigned this address to new node. So this is my new node. Okay, excellent. So this address is now sitting inside new node. And now I've said, okay, dereference new node and go to data and add whatever I've sent it to that function with. So dereference my node, dereference here the data element and add the 7 to it, and then dereference for the next pointer and add my next to it here. So 0xBBB, which means that this one is now pointing to this one. So I've got this one pointing to this one is pointing to this first one, but now I don't want this to be the head, because otherwise I don't know where this one is. So I'm going to return this new node, and I'm going to assign the head to be that node. So I'm going to return the new node, which means I'm returning 0xccc. And when I come back to this function, it's going to assign that value to the head, which means that this is now the head. So I know where to start, then I go to 5, then I go to 1, and I've got something incredible. I've got a linked list with 3 elements. So if we run it, if this computer would stop logging me out. So let's run it. I'm now going to have 7, 5, 1. So I'm following the scavenger hunt as I go through it. Yeah? No? Yep. Can we have a poll, please? Otherwise, it's just 2 people. Thank you. I appreciate it very much. Also, like, all the people in this audience must be almost done with their assignment if you're here, or just not caring anymore. Either one is a very valid feeling. Okay, so we've got our first linked list. How exciting. And we have like 5 minutes, so I could like just sprint and add something at the tail of the list. Sprint? Hey? Can we use what? Divides. I'm so sorry, I can't hear very well. I mean, you can do whatever you want with that data. Yeah. Or say it again. Yes. We will do that. It's, yeah, manipulating linked lists is coming. Yeah, you can do, yeah, it's coming either tomorrow or next week, depending on speed with which we move. And we're going to do deleting next week. And deleting is really messy. Well, it's not messy, but it's messier. That's when you create memory leaks. Oh, I really like to see that bit confused. Why is there 2 negatives in this poll? Hey? No, don't end it. A little bit confused. Just half of you are a little bit confused, which, oh, there's only 30 people that have said that they're even, well, that's really gone down now. So remember also that this is the first introduction of a linked list. You're going to be doing stuff in your tutes as well, and we're going to be doing it in the lectures for the next 2 weeks. So it's not going to be, you're not just going to be left to just kind of go on your own and that's it. So are we feeling it's too much to add something now again? Yeah? Is everyone done? Is everyone cooked? Yep, everyone's cooked. Okay. All right, we're going to do tomorrow. Then what we'll do is we'll add to the end of the linked list, and we'll start finding values in a linked list tomorrow. Thank you for showing up. Good luck with getting your assignment finished and submitted. Remember to give often and give early. And I'll see you all tomorrow online.